Hello everyone, this is Shuro. I work on PTVS and today I'm going to briefly cover MPI and MPI debugging support in PTVS. So the prerequisites for what you need to do MPI programming are obviously PTVS and Visual Studio. Then you need HPC SDK. This is the Windows HPC SDK that essentially provides you the necessary headers and the actual MPI communication library. Then you need HPC Pack. This is essentially a management console to see what's going on with your cluster or local machine. Um, and then you need wrappers. For CPython, you can use MPI4Py, and for IronPython, you can use MPI.NET. And I'll provide you links to all of these a little bit later on. So let's get started. Okay, so let's download the HPC Pack SDK. This provides you with the MPI library and the headers and a few other goodies. Make sure, by the way, you choose the right ones, 64-bit or x86. Then you need the HPC Pack. This is essentially the management console that enables you to manage a cluster, activate some nodes, pause them, look at your jobs, potentially cancel a job or resubmit it, etc. And then you need wrappers. For CPython, you can use MPI4Py, and for IronPython, you can use MPI.NET from Indiana University. So go ahead and copy the sample program from the Codeplex documentation pages to PTVS, and let's look at the code. This is essentially the hello world of MPI programming, where we're trying to calculate value of pi by throwing darts into a circle bound by a square and looking at the ratio of darts inside and outside the circle. Here we have CPython, so we're importing MPI from MPI4Py wrappers. Make a call, com.getSize, essentially talks to the runtime and says how many instances of me are there. So if you run this with 64 processors or 64 nodes, that's the value that you would have. And here rank says what is my particular task ID or processor number, so that while you're executing you can examine that. Generally the rank for basic MPI programming is done for the special case of rank 0. So you would say, hey, if I'm rank 0, do something special, otherwise I'm just another slave doing my portion of the sub calculation. And here's a global operation com all reduce, where you're getting the values that each of the processors has gathered, and then the operator you apply to it is sum. Okay, and at the end of it, you say if com.getRank is 0, I've calculated pi, and you do a finalize. To start your debugging session, go ahead and Alt-Enter on the project, go to the Debug tab, and these are the values that you need to specify. Generally, most of them are filled out for you. Whether you're 32 or 64, you specify here, publish before run true, and a path to the Python interpreter that's actually going to execute your file. Other information regarding the MPI runtime, you can click over here, and first you need to specify your head node. In this case, I've specified localhost, which is my laptop, the number of processors you want to, this is like the com.getSize, the number of processors you want to have, and you can ignore the rest since this is just a local machine. So you said OK, Control S, save stuff, go back, set a breakpoint somewhere, and just hit F5. So I just hit F5, and you should see 4 pop-ups, each of them being an output window for the ranks. If you go to the processor windows, you should see 4 processes, and the rank variable is special. This is the thing that tells you which of the SPMD instances you're in. And each time I hit F5, the execution, if you notice here, the arrow will jump around between whoever got to that breakpoint, and the rank variable here will be adjusted accordingly. So after I've hit this 4 times, you'll see the program has ended, i.e. we executed MPI finalize down here, and I will hit any key to continue. And if you go to the output tab, you will see that we've calculated pi to be 3.4 on 4 processors based on this message right here, and all the threads have exited. So that's just basic SPMD style programming on a single machine, which could have a single processor or multi-processors. MPI does support parallel processing on a single box with multiple processors. So if you have a big fat box with 12, 28, 32 cores, it's fine to use MPI programming on it. So now let's go to the cluster version of this. The cluster version really is not much different. Just go ahead and go to the configuration page for your debugger. One thing I forgot to mention is to make sure you choose the MPI cluster launcher. This is important when you do MPI programming, obviously. So again, go ahead and to the configuration. This time, go ahead and choose a head node for a cluster that you have. I'm going to choose Layton 00. And once I hit enter, what will happen is that PTVS will talk to the Active Directory, get some information about Layton, and here they are. We can see it's got a number of nodes and information about the CPU speed, how much memory each one has, and how many cores, and what the status is. And here's where I can go and specify the number of processors I need. Let's say we go with 16. All right, and the type of scheduling you want to do can be per core, per socket, or per node. Generally, you just want to leave this as core. You might want to sometimes put it as node when you have an MPI program that internally, let's say, calls a concert runtime or an OpenMP runtime, and you want to do local level parallel processing of your own. But for now, just leave it at core level. And then you have an option of which nodes to pick on the cluster. So your sysadmin may have chosen different classes of clusters. For now, just leave them as compute nodes. And you can go manually select some specific ones if you like. Let's say these 3 have GPUs installed, and you want the job to just go to those 3, because let's say you're using PyCUDA, for example. So for now, since we don't have any of that, we don't care which resources are picked as long as we get 16 processors, and now we're set up to actually execute the job. Okay, so before we hit F5, let's go ahead and take a look at the cluster. So I'll go over to the cluster manager, and this is what you get from the HPC pack. I've connected it to the head node Layton. So here we see just specify Layton. I've already done it. I see that I have in my jobs I have no active jobs currently. You can look at your finished jobs, anything that failed or canceled. Now, important thing here is that you've already installed Python on all the nodes on your cluster. The cluster manager comes with a bunch of utilities that allow you to install stuff, remove stuff, run jobs from a command line, or you can do it through APIs from your program, which is essentially what PTVS is doing. So let's go ahead and switch to our program. It's the same exact program that I ran locally, except this time when I hit F5, if you notice here, I'm publishing it to the cluster, and as soon as it's done, we should see a job appear, and here it is on the cluster, and you see there's a progress bar. it says that I've requested 16 cores, and if there are 16 cores available on the cluster, the job will continue. If there's not enough resources, it'll just get queued. And once somebody else's job finishes, you will get scheduled. And Cluster Manager, you can click on a job to find out more information about what's going on. You can see the tasks within a job. There's like preparation and copying jobs, etc., etc. And eventually all the communicating nodes will talk back to PTVS, and you can continue with your debugging, this time on a cluster. So if you notice, we've got all our ranks here, all 16 of them. Some of them are in paused state, some of them are at a breakpoint. In this case, rank number 2 is at this breakpoint, and you can look at the locals. You can have a watch window. So as I hit F5, execution will continue to a different rank, and after about 16 times, we should hit all of the breakpoints for each of the ranks, and the program will come to an end, and we should have pi calculated. So everything's running now. Program execution ends. All the tasks are cleaned up. Let's go back to the cluster. You will see that it's finished. We look at our finished jobs, and we see that it's successfully finished on 16 cores. And now if you go to the output window, we'll see some messages from the job submission process to the cluster. And if you go to the debug output, we see that we have calculated pi to be 3.138 on a very expensive cluster. Actually, art joking aside, you can put together a very nice, powerful cluster for about $400 or $500 a node. So 10 node cluster for about $5,000, 4 to 8 procs each, 4 to 8 gigs of RAM. Maybe even add some GPU cards to it later, and use PyCUDA, and you have something that's way more powerful than even Cray supercomputers from a few years back. Even before doing that, if you have some idle machines sitting in the office, you can actually rope them together and create a cluster using the cluster manager. So your cluster can be essentially an SMP box locally for your testing. It can be a bunch of idle workstations, let's say people are not using the machines at night, or you can have a dedicated cluster. And in the future, we hope to actually have support for running MPI code in Azure as well. And that's MPI and MPI debugging for you. And last but not least, we should touch on profiling, which is a subject of a different screencast, but briefly, there is profiling in PTVS for standard Python programs. And if you have MPI programs, Windows HPC has support for profiling. Profile data is collected and clock synced across all the nodes for you, and then you can view it viewing the profiling information using one of the profilers, such as JumpShot here, or Vampire, where here you have the ranks versus time, showing who's communicating with whom. You can zoom into these time slices and figure out whether how much time is being spent in your application versus the communication library, where your bottlenecks might be. This is a process-to-process view, and various high-level and lower-level viewing of your performance data, and you can zoom in and remove any hotspots. And thank you very much.